Firstly, good evening everyone. Today we are going to discuss the chapter that is hard and soft acids and bases. The terms acid and bases are routinely used in our daily life. Chemist has been classifying substances as acids and bases since long time. Lavoisier noted that the common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed that the all acid contained hydrogen. It was in 1884 Arrhenius, a Swedish chemist, developed the theory of acids and bases, known today properly as Arrhenius theory of acids and bases. According to the Arrhenius, an acid is a substance that gives hydrogen ion in aqueous solution, and a base is a substance which gives hydroxyl ion in aqueous solution. The strength of an acid and a base depend upon its capacity to provide H positive and OH negative ion respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative is in equilibrium with H2O. In 1923, J.N. Brosted in Denmark and T.M. Lowry in Great Britain independently proceed a new acid-base theory. According to this theory, an acid is a proton donor whereas a base is a proton acceptor. The acid-base reaction is regarded as proton transfer reaction. In 1923, G.N. Lewis gave another different definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor, while a base is an electron pair donor. The earlier definition of acids and bases were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to the substance that have a sharp or sour taste, turn blue litmus rag, react with certain metals to liberate hydrogen gas, and have the stability to dissolve substances insoluble in water. On the other hand, the term base was applied to the substances that have a bitter taste, soapy feel, turn red litmus blue. However, tasting and feeling chemicals are dangerous method of determining whether the substance is an acid or a base. You should never ever taste or touch solutions of chemicals in a laboratory. There are, however, other methods of recognizing acids and bases. For example, acid and bases change the color of the certain dyes non-popularity as indicators. On the most common indicator is a vegetable dye obtained from the lichen known as litmus. Aqueous solution of acids turn litmus red, whereas aqueous solution of bases turn it blue. Thus, any substance which has an unshared pair of electrons can act as a Lewis base, whereas substances which have an empty orbital to accommodate a pair of electrons act as a Lewis base acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis bases, and a substance capable of accepting a pair of electrons are regarded as Lewis acids. Acid-base or neutralization substitution reaction may thus be regarded as donor Lewis base, acceptor Lewis acid. Reaction or coordinate covalent bond formation reactions. The classical example of Lewis acid-base reaction is that of between boron trifluoride and the ammonia. Using electron dot diagram, we can see that boron trifluoride is the Lewis acid and ammonia is the Lewis base. Lewis base ammonia plus BF3, which is Lewis acid, coordinate bond is formed NH3 and BF3. Donor acceptor or coordinate bond formation reaction. Lewis concept of acid and bases is very commonly used because of its simplicity and the ease with which the formation of coordinate compound can be explained. In brief, all the usual ligands can be regarded as Lewis bases, whereas all the metal ions can be regarded as Lewis acids. The degree of affinity of a metal ion for ligand can be termed as Lewis acidity, and the tendency of the ligand to combine with the metal ion can be regarded as Lewis basicity. Hard soft acids and bases. An acid-base reaction, according to the Lewis concept, involves the reaction between a donor A and an acceptor as form a complex ion. A plus B coordinate bond is formed between A and B. The formation of the stable complex between the donor A and the acceptor B depend upon the nature of the species A and B involved. It has been known since long that certain ligands form more stable complexes with metal ions such as Ag positive, Ag2 positive, palladium 2 positive and platinum 2 positive. On the other hand, certain ligands form stable complexes with metal ions such as Al3 positive, cobalt 3 positive and platinum 4 positive. Based upon the preferential bonding, the acids and bases have been classified into two groups, with class A and class B according to their preferences. Class A metal includes alkali metals, alkaline earth metals, lighter and more highly charged ions, for example, titanium 4 positive, chromium 3 positive, Al3 positive, H positive ion. Class B metal ions include heavier transition metal of second and third transition series, which cadmium 2 positive, Ag2 positive, palladium 2 positive, platinum 2 positive. Heavier transition metal in lower oxidation state, Ag positive, Ag2 2 positive, copper positive. Low valent metal ions such as zero valent metal in metal carbonyls. Depending upon the type of metal ions, ligand can also be classified as class A or class B depending upon the preference. Class A ligand includes molecules or ions with donor atoms nitrogen, oxygen, fluorine, chlorine, etc. It is important to note that class A ligand prefer to form strong complexes with class A metals. Class B ligands including molecules, ions with donor atom phosphorus, arsenic, sulfur, selenium, iodine, etc. Class B ligands prefer to form complexes with class B metal ions. It was in 1963 Pearson coined the term hard and soft acids and bases for class A and class B metal ions and ligands respectively. Accordingly, class A metal ions are referred to as hard acids, while class B metal ions are called the soft acids. Similarly, class A ligands are named as hard bases, whereas class B ligands are termed as soft bases. In summary, according to the Pearson, class A acids are hard acids, H positive, Li positive, Na positive, beryllium 2 positive, magnesium 2 positive, chromium 3 positive, iron 3 positive, etc. Class B acids are soft acids, Ag positive, palladium 2 positive, copper positive, platinum 2 positive, etc. Class E bases are hard bases. Class A bases are hard bases H2O, NH3, fluorine negative, ROH, etc. Class B bases are soft bases R3P, R3AS, R2S, R2SE, I negative, SN negative, etc. Classification of acid and bases as hard and soft. Pearson observed that it is possible to correlate acid-base interaction on the basis of hard and soft acids and bases. He observed that type A metal ion acids were small, compact and not easily polarizable, and thus preferred ligands that were also small and less polarizable. He called these acids and bases as hard. On the other hand, type B metal ions and the ligand they prefer appear to be large in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship, expressed that hard acid prefer hard bases and soft acids prefer soft bases. Classification of acids, a general classification of some common hard and soft acids along with some borderline cases in given this table. In table, hard acids include H positive, Li positive, Na positive, K positive, beryllium 2 positive, magnesium 2 positive, calcium 2 positive, strontium 2 positive, aluminium 3 positive, scandium 3 positive, gallium 3 positive, indium 3 positive, lanthanum 3 positive, Cr 3 positive, cobalt 3 positive, Fa 3 positive, As 3 positive, cerium 3 positive, silicon 4 positive, titanium 4 positive, zirconium 4 positive, thallium 4 positive, Pu 4 positive, Bf3, Bcl3, Alcl3, Alh3, Al, CH3 whole thrice, Cl3 positive, Cl7 positive, I5 positive, I7 positive, RCO positive, CO2 and Nc positive. Soft acids include copper 2 positive, Ag positive, Au positive, Ti positive, Hg positive, platinum 2 positive, cadmium 2 positive, platinum 2 positive, H mercury 2 positive, platinum 4 positive, titanium 3 positive, boron BH3, GaCl3, gallium trichloride, gallium tribromide, gallium triiodide, I positive, bromium positive, OH positive, RO positive, I2, Br2, ICN, O oxygen, chlorine, bromine, iodine, nitrogen, RO free radical, RO2 free radical. Borderline acids, Fe2 positive, cobalt 2 positive, nickel 2 positive, copper positive, zinc 2 positive, Sb3 positive, bismuth 3 positive, NO positive, SO2, RH3 positive, iridium 3 positive, Ru3 positive, R3C positive, Sn2 positive, Pb2 positive. An inspection of table 4.1 reveals that hard acids usually have the following characteristics. Hard acids are cations of smaller size. Hard acids are the cation of higher oxidation state. Hard acids are molecules cations with lesser number of valence electrons. Hard acids hold the valence electrons tightly and consequently are not separated, are not easily polarizable. In summary, hard acid binds strongly to a proton. Hard acids are small sized, compact and not easily polarized. A close look at table 4.1 also reveals that soft acids possess the following characteristics. Soft acids are cations of large size or heavier metals. Soft acids are cation of lower charge. Soft acids are molecules or ions with large number of valence electrons. Soft acids do not hold the hold the valence electron tightly and are therefore easily polarizable. In summary, soft acids are large-sized and easily polarizable ions or molecules that bind strongly to highly polarizable ion or a molecule. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard nor too soft acids. Such type of acids that are neither so hard nor so soft are called the borderline acids, which are shown in the extreme right of the table 4.1. Borderline acids have properties which are intermediate between that of a hard acid and a hard base. In case of borderline acids, the properties such as size, oxidation state, polarizability of the cation or molecule are neither too low nor too high. On the other hand, hard soft acids will show the opposite trend, and the following order of preferences for the binding donor atom or ion within a group is observed as I negative greater than Br negative greater than Cl negative and F negative. R2Te greater than R2 selenium greater than R2 sulfur greater than R2O. The above trend can be pictorially represented as I have told you, and the question that comes into our mind are what type of interactions do you expect between a hard acid and a hard base? Since both a hard acid and both base are not easily polarizable, their interactions are predominantly ionic. What type of interactions do you expect between a soft acid and a soft base? Since both soft acid and soft base are usually polarizable, the interaction between them are predominantly covalent. Classification of bases. A general classification of some commonly used ligands into hard and soft bases along with borderline bases is presented in table 4.2. Hard bases include fluorine negative, Cl negative, NH3, RNH2, N2H4, ROH, R2O, R2C double bond O, RO negative, H2O, OH negative, O22 negative, SO42 negative, PO43 negative, CH3COO negative, ClO4 negative. Soft bases include H negative, R negative, I negative, C2H4, C6S6, RSH, R2S, RS negative, Cn negative, Sn negative, H2O32 negative. Borderline bases include bromine negative, pyridine or aniline, N2, N3 negative, NO2 negative, NO2 negative, SO32 negative, carbonyl, RNC. A glance at table 4.2 reveals some of the important characteristics of hard bases. Hard bases bind strongly to the proton. Hard bases contain a donor atom of high electronegativity. The donor atom in hard bases possesses low polarizability. The hard bases are not easily oxidized. Hard bases contain empty orbital of high energy. In summary, hard bases bind strongly to a proton. A further inspection of table 4.2 reveals the following features are observed in case of soft bases. Soft bases contain donor atoms of low electronegativity. Soft bases contain donor atom of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low-lying energy orbitals. In brief, soft bases which contain the less electronegative non-metal including carbon, sulfur, phosphorus and iodine. The donor atoms in such bases possess donor atoms that are easily polarized. Just as there are borderline acids, there are borderline bases also. The properties of borderline bases are in between those of the soft acids and the hard bases. It is important to note that these categories are not rigidly divided. For example, the halide ion from a series from the very hard fluoride ion, though the hard borderline chloride ion, to the borderline bromide ion and the soft iodide ion. The soft acids, also known as class B metal ions, are the group of metal ions that are in the lower right portion of the metallic elements. Pearson HSAB principle. Pearson proposed a simple rule for predicting the stability of a coordination compound formed between acids and bases. This rule is quite often named as HSAB principle. According to Pearson HSAB principle, hard acids prefer to bond with hard bases while soft acids prefer to bond with the soft bases. It is important to note that hardness and softness of acids and bases refer only to hard and soft interaction. It is by no means related to the strength of acids and bases. For example, both F negative and OH negative ions are hard bases, but the basic strength of OH negative ion is 10 to the power 13 times that of fluorine ion. In just other words, hard acids will show the following order of preferences of binding the donor ions within a group. F negative greater than Cl negative greater than Br negative greater than I negative. Similarly, oxides of R2O, R2S, R2Se, R2Te, R3N greater than R3P greater than R3As greater than R3Sb. Applications of HSAB principle. Pearson principle of HSAB has a number of applications in inorganic chemistry. Some of these are discussed below. First is stability of the. We have already noted that hardness and softness of acids and bases are related only to the hard and soft interactions. Hardness and softness of acids and bases has nothing to do with the inherent acidic or basic strength of the acids or bases. For example, both OH negative and F negative ions are hard bases, although OH negative ion is the stronger base than F negative ion. In fact, OH negative is 10 to the power 13 times more stronger a base than the F negative ion. However, in HSAB principle, both OH negative and F negative ion are at the par with each other. Pearson in 1963 explained the relative stability of the coordination complex on the basis of HSAB principle. Let us consider a general reaction between a Lewis acid and a Lewis base. Let the Lewis acid is A and the Lewis base is B, and a complex is formed between A and B. The complex A will be more stable if A and B are either both hard or soft. The complex AB will be less stable if A is hard and B is soft, or A is soft and B is hard. For example, complex between a soft acid Ag positive and a soft base I negative ion is quite stable in contrast to one between a soft acid Ag positive and a hard base F negative. Ag positive, which is soft acid, combined with 2I negative and form the complex AgI2 whole negative. Ag positive, which is soft acid, combined with 2F negative, which is a hard base, form the complex AgF2 negative, which is the unstable complex. Similarly, the reaction between LiI and CSF resulting in the formation of LiF and CSI constitute an interesting example suggesting the preferential stability of soft and hard combinations. Lithium iodide plus cesium fluoride form the lithium fluoride and the cesium iodide. Lithium iodide, which is hard soft, cesium fluoride, which is soft hard, form the complex that is lithium fluoride, which is hard, and the cesium iodide, that is the soft. Some of the other important reactions suggesting the stability of the soft and hard interactions as given below. Copper iodide, hard soft, which is hard soft, copper fluoride, which is soft hard, form the complex copper fluoride, that is the hard, plus 2 copper iodide, which is soft. Similarly, calcium sulfide plus H2O form calcium oxide plus H2S. The role of a thumb in determining the stability of the complex is the preferential formation of the hard and soft interactions. Now, the second basis is classification of acids and bases. The acids and bases can be classified as hard or soft depending upon their preference for hard and soft reactants. Let us consider the following reactions: BH positive plus CH3Hg positive form the complex CH3HgB positive plus H positive. We already know that H positive is a hard acid, whereas CH3H positive is a soft acid. If boron happens to be a hard base like NH3, the reaction on the left hand side will be preferred. NH4 positive plus CH3H positive is formed when the reaction between CH3Hg positive NH3 complex plus H positive. Conceptually, ammonia can be written as NH4 positive by the formation of NH3, which is a hard base, and H, which is a hard acid, which means the formation of NH4 positive is preferred because of hard acid H positive and hard base NH3. On the other hand, if B is a strong base like R2S on the right hand side, the reaction will be favored as shown. R2SH positive plus CH3Hg positive form the complex that is CH3Hg SR2 plus H positive. Conceptually, CH3Hg SR2 positive can be written as CH3H positive plus SR2, which means the formation of CH3Hg SR2 is preferred because of soft acid CH3Hg positive and a soft base SR2. Similarly, acid A can be classified as hard or soft depending upon the direction of equilibrium. AF plus SCN negative form the complex that is in equilibrium with ASCN plus F negative. We know F negative is a hard base and SCN negative is a soft base. If A is a soft acid like Ag positive ion, then the above reaction in the forward direction is favored. AgF plus SCN negative form the complex AgSCN, which is soft plus F negative, which is a hard. Conceptually, AgSCN is formed through soft interaction. Hence, according to HSAB theory, the reaction is preferred in the forward direction. On the other hand, if A happens to be large hard acid like Na positive ion, thus the forward reaction is not favored, rather than the backward reaction is preferred. In this, NaCN plus, which is hard soft, plus F negative, which is hard base, form the complex that is SCN, which is soft, and plus NaF, which is hard and hard. Conceptually, NaF is formed through the hard interaction. Thus, according to HSAB theory, the reaction is preferred in the backward direction. OH negative is much stronger base than SO3 2 negative and hence cannot be displaced by the water have SO3 2 negative. Thus, the reaction, however, is favored by the HSAB principle. CH3 cadmium OH plus SO3 2 negative form the complex that is CH3CD SO3 negative plus OH negative. It is important to conclude at this stage that Lewis acid Lewis base reactions are governed by the two independent principles with strength of acid or base, softness and hardness of acid or base. The definition of hardness: primarily uses an idea of polarizability, which states that a low polarizable species is hard and a more easily polarized is soft. For ions of similar size, the ratio of charge to radius should be used to assess the relative polarizability. However, HSAB should be used to does not sorry however HSAB principle does not take the consideration the permanent idea of relative hardness and softness of the species. In summary, the major limitations of HAB principle are: HSAB principle is too general and without any qualitative scale of the measurement. HSAB principle does not take HSAB principle failed to explain the feasibility of the reaction. Limitations of HSAB principle. The hardness and softness of an acid or a base is primarily related to stability of the hard and the soft interactions. It has no concern with the acidity or basicity of the acid or base. For example, OH negative and F negative are well known hard bases. However, the basicity of the hydroxide ion OH negative is very large as compared to the fluoride ion. In fact, the basicity of hydroxide ion pK equal to 15.7 is 10 to the power 13 times that of the fluoride ion, whose pK value is 2.85. A strong acid or a strong base is well known to displace the weak acid or a weak base. For example, the reaction between a sulfite ion and hydrogen fluoride proceeds in the forward direction. It means that the stronger bases SO3 negative can easily displace the weaker base fluorine negative ion from the acid hydrogen fluoride. Sulfide ion plus HF displaces the reaction and the equilibrium is established, and then HSO3 negative plus F negative ion is formed. However, the above reaction is not favored according to HSAB principle as detailed below. SO3 negative, which is soft base, plus HF, which is hard base, form the reaction product HSO3 negative, which is hard soft, plus F negative, which is hard base, which only favor hard and soft interactions. Similarly, a very strong base OH negative can displace a weak base from a soft acid methyl mercury 2 cation. OH negative, which is hard base, plus CH3HgSO3 negative, which is soft, is in equilibrium with CH3HgOH, hard soft, and SO3 negative, which is soft bases. However, the above reaction is not favored according to HSAB principle, which only favor hard or soft interactions. In both the above cases, 4.1 and 4.2, it is the inherent strength of the bases SO3 negative, F negative, and OH negative and SO3 negative that forces the reaction in the forward direction in spite of less preferred formation of hard-soft pairs in the product. This is true in case especially when the inherent strength of base being compared are simply different. The order of basic strength being OH negative 15.7 greater than SO3 negative, which is 6.8, and F negative, which is 2.85. In other words, significant different basic strength forces the reaction 4.1 and 4.2 against the wishes of hard-soft interactions. However, when both the strength of the acid and base are and hardness, softness are not simply different, when HSAB works well, resulting in product having hard and soft combinations. For example, CH3HgF, which is soft hard, plus HSO3 negative, which is hard soft, is in equilibrium with CH3HgSO3 negative, which is soft plus HF, which is hard, whose K value is 10 to the power 3. and CH3 HgOH, which is soft hard, plus HSO3 negative, which is hard soft, is in equilibrium with CH3 HgSO3, which is soft soft, plus HOH hard, whose K value is given by 10 to the power 7. It is important to mention that the inherent strength of acid and bases should not be ignored while applying HSAB principle. Symbiosis. What is symbiosis? The hardness or softness of an acidic or basic center is not an inherent property of an atom, but depend upon the substituents. Thus, ammonia is a hard base while pyridine is a borderline base. The acidic B3 positive is a borderline between a hard and a soft acid. Addition of 3 small sized non-polarizable substituents like fluorine ion make it a hard Lewis acid, that is BF3, whereas addition of electron donor and easily polarizable group like H negative ion, hydrogen ion, and make it a soft Lewis acid, that is the BH3. The difference in the hardness and softness of BF3 and BH3 can be illustrated nice in the following examples. R2S dot BF3, which is soft hard, plus R2O, which is hard, form the complex R2O BF3, which is hard, plus R2S, which is soft. And second example is R2O BH3, which is hard soft, plus R2S, which is soft, form the complex R2S dot BH3, which is soft, plus R2O. Jorgensen in 1968 observed that hard acids have a tendency to combine with a metal ion having hard ligands and soft ligands, and have a tendency to combine with a metal ion already having soft ligands. He coined the term symbiosis for such interactions. The hard BF3 molecule prefer to combine with a hard base F negative ion to form tetrafluoroborate BF4 negative, whereas soft acid BH3 prefer to combine with soft base H negative ion to give tetrahydroborate ion. BF3 plus F negative give the tetrahydroborate ion, and BH3 plus H negative give the BH4 negative ion, and B2H6, which is soft acid, plus 2H negative, which is soft base, form the complex 2 moles of BH4 negative. An important outcome of symbiosis is that symmetrical substituted compounds are found in preference to the unsymmetrical substituted compounds. For example, compound containing mixed substituents interact strongly to yield symmetrical compounds with the same substituents as given below. BH3F negative, which is soft hard, plus BF3H negative, which is hard soft, form the complex BH4 negative, which is soft plus BF4 negative, which is hard. Similarly, mixed fluorinated methanes can be reacted to give the symmetrical methanes, which is CH3F, which is soft hard, plus CF3H, which is hard soft, give the complex CH4, which is soft plus CF4, which is hard. In brief, symbiosis may be defined as the tendency of soft ligands to combine with a metal ion already having soft ligands, and the tendency of hard ligands to combine with a metal ion having hard ligands. Now, the theoretical basis of hardness and softness, that is HSAB principle. A number of theories have been proposed to explain the preference of the hard acids toward hard bases and soft acids toward bases. First is the electrostatic interaction theory. According to the theory, hard acids and hard bases form purely ionic compound. Therefore, hard interactions are purely ionic or electrostatic. Most of the hard acids such as Li positive, Na positive, K positive, etc. and hard bases such as O2 negative, F negative and OH negative, etc. are well known to form ionic compounds. We know that the electrostatic energy of an ion pair is inversely proportional to the interatomic distance. It means the smaller the ion, the smaller will be the internuclear distance and hence greater will be the electrostatic energy between the ions. As a result, the final compound formed by hard acid and hard base will be highly stable. Second is the polarizing power or polarizability. Electrostatic interactions cannot explain the soft interactions because of the bigger size of soft ions. Therefore, the interaction between large sized acids and bases must involve covalent character. For example, soft acids such as Ag positive, Hg positive, Cu positive, etc. form strong compounds with soft bases like H2 negative, I negative, etc. which has substitutional covalent character. Almost all the soft acids have 6 or more d electrons. Soft acid with D10 configuration are excellent soft acids. Example, Ag positive, Hg2 positive. It is these d electrons that have mole polarizing power. Secondly, the soft bases like H2 negative and I negative are easily polarizable. Thus, the bonding between soft acid and soft bases is largely covalent. Now, the third theory is natural occurrence of the ores and the minerals. The natural occurrence of ores of certain metals can be easily explained on the basis of HSAB principle. Hard acid metal ions such as Mg2 positive, calcium 2 positive, Al3 positive, Fe3 positive, chromium 3 positive, etc. frequently occur as their oxide, fluoride, chloride and carbonate. This is primarily due to their preferred hard acid hard base interactions. We know that oxides O2 negative, halides F negative or Cl negative and carbonates CO3 negative are all hard bases. These hard acid metal ion cannot occur as sulfides H2 negative because H2 negative is a soft base and cannot form stable compounds. On the other hand, soft metals such as copper positive, Ag positive, cadmium 2 positive, Hg2 positive, palladium 2 positive, etc. occur invariably in ores as their sulfides due to their soft soft base interactions that result in formation of the stable complex. Interestingly, the borderline acids like CO2 positive, nickel 2 positive, Pb2 positive, zinc 2 positive can occur both as sulfide as well as their oxides or carbonates, which is hard bases, as a result of their intermediate character. Now, the fourth property is catalytic poisoning. All metal atoms are soft acids. Some of the metal, namely vanadium, chromium, nickel, palladium, platinum, molybdenum, etc. are well-known catalysts. These metal catalysts have been found to be easily polarized by the soft bases which carbon monoxide, unsaturated hydrocarbons, olefins, alkynes, dienes and arenes, organophosphine R3P and organoarsines R3As, etc. This poisoning is contributed to the soft acid soft base interactions between the metal atom and the soft ligand. In fact, these soft ligands are adsorbed strongly on the surface of the metal and block the reactive sites by forming metal complexes. In other words, the metal atom loses their activity and are said to be poisoned. Thus, soft bases complexes with the metal in atomic state will act as poison toward metal catalysts. Now the third topic is the electronegativity and hardness and softness. Hardness and softness are related to electronegativity. Species with higher electronegative values are assigned greater hardness and those with lower electronegative values are assigned as greater softness. Electronegativity conventionally means the power of an atom in a molecule to attract toward itself. However, in this case, it refers to the power of an individual ion participating in a reaction. For example, lithium atom is known as highly positive, metal, but the cationic species Li positive has a greater tendency to attract electron toward itself. As a result, Li positive is considered to be the most electronegative and hence is a hard acid. On the other hand, heavy transitional metal ion in low oxidation state like copper positive, Ag positive, Hg positive, cadmium positive, etc. have relatively low strength have relatively low second ionization potential and the consequently possess low values of electronegativity. As a result, these ions are considered as soft acids. Using the same concept of electronegativity, we can define hard and soft bases. The relationship between hardness and electronegativity can be explained several important features as why CF3 is harder compared to methyl group. Boron trifluoride is harder compared to borane. Ammonia is harder than trimethylamine. Trifluorophosphine is harder than phosphine, which is in turn harder than trimethylphosphine. Milligan-Jaffe defined electronegativity as a linear function of the partial charge developed on an atom according as chi is equal to A plus B delta. A refers to the electronegativity of the atom, B refers to the rate of change of electronegativity with charge. The electronegative value A of the atom is similar to the Pauling or Alford-Roscoe and the parameter B is called the charge coefficient. Smaller hard and non-polarizable atoms have higher value of B, whereas large soft and polarizable atoms have smaller value of B. Parr and Pearson introduced a new term called the absolute hardness for neutral as well as charged species and correlated it with the absolute electronegativity. The absolute hardness is defined as half the difference between ionization energy and the electron affinity. We know Millikan definition of electronegativity is chi is equal to I plus A by 2. The hardness of base B and acid A may be defined as eta B is equal to eta of species B plus equal to half into B positive minus AB positive. Eta of species A equal to half of IA minus affinity of A. In order to understand as to why the equation 4.6 the base B is represented as B positive whereas in equation 4.7 acid A is represented as A. Let us consider the interaction of acid and base B to form the compound AB. In the formation of compound AB, the electron will move from B to A, which is indicated by partial delta positive and delta negative charges. Hardness of B refers to a species giving from delta positive to a charge 1 plus delta positive on ionization, while hardness of A refers to the species on ionization from delta negative to a charge 1 plus delta negative. If the shift of the charge delta is taken as equal to 0.5, then the charge on B becomes 1.5 and then on A becomes 0.5. Thus the charge on B changes from 0.5 to 1.5, which on average give one value, and that a charge on A shift from minus 0.5 to 0.5 with average equal to 0. That justifies the region why species B is taken as B positive and a neutral atom A. In close inspection of table 4.5 and 4.4 and 4.5 reveals that the absolute hardness values are in good agreement with their non-chemical behavior. Hydrogen is the only exception which is different in all the three tables 4.3 and 4.4 and 4.5. It is advisable to consider it as a special case. With the exception of H negative, the values of hardness parameter of all other bases as expected. The hard bases F negative and OH negative have large value of eta B, while the soft bases SH negative and CH3 negative have smaller values. The hard acids such as Na positive, Mg2 positive, Al3 positive have large eta A values, whereas the soft acids such as Ag positive, copper positive, Au positive has small eta A values. Borderline acids borderline metal ions such as manganese 2 positive, iron 2 positive, nickel 2 positive, copper 2 positive, zinc 2 positive have intermediate values. It is interesting to note that down a column in the periodic table from the magnesium 2 positive to barium 2 positive, there is steady increase in the softness. Similar observation of softness is made in going from nickel 2 positive to palladium 2 positive. This is also an expected increase in hardness values with increase in the oxidation state as Fe0 की वैल्यू है 3.87, Fe2 पॉजिटिव की 7.30, Fe3 पॉजिटिव की 13.10. थैंक यू.